In general, we can hook up capacitors or resistors in one of two ways. Right now we'll focus on capacitors, and we'll start with capacitors in parallel. A parallel circuit, we'll start with our battery, which I just drew. And our capacitors. So when we take a look at the circuit, each capacitor is on a different rung, so it looks like a ladder. Each of those rungs are in parallel with each of the others. Now, this parallel line that I've drawn here, this is the symbol for a capacitor when we're looking at a circuit diagram. And the script E I have inside the battery, that represents the EMF of the battery. Now recall that the potential difference over the battery is equal to the EMF of the battery, in the case of an ideal battery, which we will assume we have here. So let's go ahead and take a look at the potential at some various different points in this circuit. So I'm marking some points along my circuit so we have something to refer to. Now notice, as we work along the top part of my circuit, points 1, 2, 3, and 4 don't have anything between them, just some wire. So with an idealized wire, we can say that the potential at each of these points is equal to each other. Same goes for the bottom half. Now, that means that the potential difference over each one of these capacitors must also be the same. So, for capacitor 1, the potential difference over that, which is from point 2 to point 7, so the potential difference between point 2 and point 7 is equal to the potential difference between points 3 and 6, and the potential difference between points 4 and 5. Now remember from the previous video that charge is related to the potential difference and the capacitance of the capacitor. So the charge on the plates of capacitor 1 is going to be equal to the capacitance of capacitor 1 times the potential difference over those plates. And since each of the potential difference over each of our capacitors is the same, I'm going to call this V sub C. The charge on capacitor 2 will be related to the capacitance of number 2, again, times the potential difference, and same with 3. The total charge, Q, is then going to be the sum of the charge on each one of these capacitors. Because my battery is escalating charge up its little escalator, we can deposit different amounts of charge on each one of those capacitor plates. Now, if we want to replace these 3 capacitors with one equivalent capacitor, it would have to have the total charge Q and the potential difference delta V sub C. So the equivalent capacitor that could replace all 3 of those would have total charge Q, and the potential difference would be the same as what we already have, delta VC. Now relating this back to the capacitors, the capacitance of the capacitors that I already have, this is just C1, this is C2, and this is C3. So an equivalent capacitor, to replace each of my capacitors that I have listed in parallel right now, would have a capacitance that has to be the sum of however many capacitors I have in my circuit. And again, this is for parallel capacitors. Capacitors in parallel. Not to be confused with parallel plate capacitors. Now, if instead of capacitors in parallel, we have capacitors in series, again, we'll have a battery with the same EMF. Capacitors in series are basically all in a row. Now, in this example, in series, the potential difference between points 1 and 2 is not necessarily the same as the potential between points 2 and 3, which is not necessarily the same as the potential between points 3 and 4. But if we're putting charge Q on the top plate here, that means in order to keep the same potential difference that we have over the battery as we have between points 1 and 4, then the very bottom plate here has to have charge negative Q. And if this bottom plate has charge negative Q, then that's going to induce a separation of charge. The top plate has positive Q, which means that the bottom plate of capacitor 2 has to have minus Q, which is inducing a charge. The top plate with positive Q, and then again we end up with a negative Q on the bottom plate of capacitor 1. So, looking at this, each capacitor has the same charge Q. So, whereas when we were talking about capacitors in parallel, they all had the same potential difference, capacitors in series all have the same charge. That means that the potential difference across each capacitor has to be different, and in fact it's going to end up adding to the EMF of the battery. So let's write out what each of these potentials must be. The potential difference between points 1 and 2 is going to be equal to the charge on the capacitor divided by the capacitance. And similarly, we'll find relations for each of the other capacitors. Now, because we have a closed circuit, the potential difference between points 1 and 2 plus the potential difference between points 2 and 3 plus the potential difference between points 3 and 4 minus the EMF of the battery have to equal 0. So we can rewrite this as the EMF of the battery has to equal the sum of the potential difference at each one of these points. So we're going to call this delta V sub C. Then, the equivalent capacitance for capacitors in series has to be the charge Q that is on each one of the individual plates divided by the potential difference over the capacitors as a whole. We can rewrite this using the potential difference over each individual capacitor here. Now, if we invert this equation, I will get 1 over my equivalent capacitance is equal to the sum of the potential difference over each one of those capacitors divided by the charge. Now you'll notice that this first one here is 1 over the capacitance of the first capacitor, 1 over capacitance of the second, and 1 over the capacitance of the third. So if I rewrite this, I find a relationship between equivalent capacitance and the capacitance of the individual capacitors if they are in series. When you're going through and using this equation to determine the equivalent capacitance of a collection of capacitors that happen to be in series, don't forget to invert back after you add up this sum. So a different way of writing the same thing, which may or may not help you to remember to invert, is this. Both are equivalent statements. Now, just to be clear, each one of these equations has taken the circuit diagram that I showed before for both series and parallel capacitors and found the capacitance where the entire circuit could be rewritten or redesigned so there was only one single capacitor that happened to have the equivalent capacitance of all of the individual ones, whether they were in series or in parallel. We'll do more examples in class where we can go through and look at this. In particular, we'll look at more complicated ones where you have capacitors in both parallel and in series.